Okay, welcome back, everyone. The last speaker of our session is Yuval Wigderson, who at some point was stolen from our mini symposium by Andre, but luckily we were able to bring him back. So he will talk on the minimum degree and the graph removal lemma.
Okay, yeah, thank you, Liana, and thank you everyone for being here, especially the people in Russia who are staying up late. So I'm going to be talking about some recent joint work with Jacob Fox, who's my advisor at Stanford. And I want to tell you about minimum degree and the graph removal lemma, but first I need to tell you about minimum degree, and then I'll tell you about the graph removal lemma, then I'll put it together, and then I'll wrap up with some nice open problems. So let's get started with minimum degree conditions. So for this slide, let's let G be a graph with n vertices, minimum degree delta of G, and let's have it be triangle free. And basically what I want to ask is, what can we say about such graphs? So probably the earliest result in this direction is the theorem of Mantel from 100 years ago, who proved basically that if the minimum degree is at least a half times n, then actually such a graph can't exist. So there does not exist a triangle-free graph with minimum degree more than 1/2 times n. And this is tight as shown by this example of a complete bipartite graph. This has minimum degree equal to 1/2 times n if the parts are balanced, and it's triangle-free. But sort of Mantel's theorem says this is the densest possible graph, the highest minimum degree that you can achieve. There's a nice extension of Mantel's theorem due to András, Erdős, and Sós. And what they proved is that if you weaken the minimum degree condition, so from 1/2 to 2/5, then graphs like this can exist, but they all must be bipartite. And again, this theorem is tight, as shown by this example. So this is a balanced blowup of a C5. This graph has minimum degree equal to 2/5 times n. It's triangle free and it's not bipartite. So basically, 2/5 is the threshold for triangle free graphs being bipartite. And another way of saying this theorem of András, Erdős, and Sós is instead of bipartite, I can say a subgraph of this structure, right? Every bipartite graph is a subgraph of this. So what you see is that, above 1/2, there aren't any triangle-free graphs. And then between 1/2 and 2/5, this is the only structure. And then at 2/5, this new structure appears. So you can maybe predict what the next theorem is going to look like. This is a theorem of Hegqvist that says that until 3/8, these are actually the only two structures. So if I have a triangle-free graph with a minimum degree more than 3/8, then it must be a subgraph of one of these two structures. And again, 3/8 is tight, as shown by this example. So it turns out this is a graph with minimum degree 3/8 times n. It's triangle-free, and it's not a subgraph of either of these. Okay, and I think you're getting the pattern. And in fact, there's a nice paper of Jin who found 7 more thresholds of the minimum degree, where 7 new structures appear at each time. And I think the best way to think about these theorems is with a picture. So here's a schematic. On the x-axis, I'm putting the minimum degree condition, so the minimum degree divided by n, and sort of vertically, I'm going to draw the structures that can appear for triangle-free graphs. So the first thing we said is that there's a threshold at 1/2 where there just is nothing to the right of 1/2. There are no triangle-free graphs with minimum degree more than 1/2. But then at 1/2, this bipartite structure appears. And for a while, this is the only structure. But then at 2/5, another structure appears, which is this blowup of a pentagon. And then for a while, the only graphs are subgraphs. The only triangle-free graphs are subgraphs of these two. But then at 3/8, this graph appears. The first of Jin's theorem is that at 4/11, there's this graph that appears. Jin found 6 more of these thresholds. Turns out there's a very special threshold at 10/29 where this unbalanced blowup of the Grich graph appears. Whatever, and this keeps going. And you could ask, how long does this keep going? So how much can I push the minimum degree while still only having like a bounded set of structures that can appear? And it turns out that it doesn't go on forever. So it turns out that there's something happens at 1/3, and below 1/3, there's actually unbounded complexity. So I want to make this rigorous and tell you what actually this means. So what happens at 1/3? So the first theorem here is due to Erdős, Heinl, and Szymonovich. And what they proved is that for every positive alpha, there exists a triangle-free graph with minimum degree at least 1/3 minus alpha times n. So as close to 1/3 as you want from below, but it has unbounded chromatic number. And so in particular, if it has unbounded chromatic number, it can't be a subgraph of some like fixed blow-up structure. So basically, this is what I was saying, that below a third, suddenly you can get sort of arbitrarily complex graphs where complexity is measured in high chromatic number. And the matching upper bound was used Thomasin about 20 years later. And Thomasin just proved the corresponding theorem that actually the threshold is at a third. So if instead I assume that I have a triangle-free graph with minimum degree just over a third, so a third plus alpha, then it must actually have bounded chromatic number. And so from this perspective of when does the chromatic number of triangle-free graphs start being bounded, really a third is the threshold. And this is closely related to what I was drawing in the previous picture, but a sort of better way of saying this is due to Wuchak. And Wuchak proved sort of exactly the picture I had on the previous slide. So if I assume that I have minimum degree above a third plus alpha, then there's actually a finite set of triangle-free graphs such that my graph G must be a subgraph of a blowup of one of those graphs. So these are exactly the finite structures that I had on the previous slide, like the complete bipartite thing or the pentagon and so on, that if I'm at any point above a third, a triangle-free graph must be a subgraph of a blowup of one of a finite list of structures. And these theorems started a large line of work, and there are names for these things now. So these first two theorems say that the chromatic threshold of the triangle equals 1/3. So I haven't defined this formally, but what this means is that 1/3 is the threshold where triangle-free graphs go from having bounded chromatic number to unbounded chromatic number. And similarly, this theorem of Wuchak now goes under the name that the homomorphism threshold of triangle-free graphs equal a third. So basically, at a third is when triangle-free graphs have one of these bounded set of structures. Okay, so that's everything I wanted to say about minimum degree for the moment. Now I want to move to something totally different and tell you about the removal lemma, and then I'll come back and put this together. Okay, so up to now I've been talking about graphs that have no triangles, but can we say anything if we only assume that we have a graph that has few triangles? And in some sense, the answer is yes. I'm sure many of you have heard of this triangle removal lemma of Ruja and Semeredi. And what their theorem says is that if I have a graph that has few triangles, so at most a row n cubed triangles, then it can be made triangle-free by removing a small number of edges, epsilon n squared edges. And so one way of thinking about this is that if I want to understand graphs with few triangles, it suffices to understand graphs with no triangles. Sort of another way of saying the triangle removal lemma is the only way to produce a graph that has few triangles is to start with a graph that has no triangles and then to add a small number of edges. And because of this, if you want to understand graphs with no triangles, with few triangles, it's sort of okay to understand graphs with no triangles. And the removal lemma is a really important result, and it has many applications in number theory, computer science, graph theory, and many other fields. And one thing that I want to stress about the removal lemma is that despite this very simple statement, all the known proofs are very hard. So when you see a statement like this, you might expect that you could just prove it by some easy sort of averaging or something like this. And we don't know how to do that. So all known proofs rely on something like Semeredi's regularity lemma. It uses some heavy machinery. And I just want to mention on this slide, there's nothing special about triangles. So this was extended independently by Alon Duke, Lefman, Rudel, and Euster, and by Ferretti. And they just proved the corresponding statement for removing copies of H. So it's the same thing. If I have a graph that has few copies of some fixed graph H, then we can make it H-free by removing few edges. Okay, and I want to dwell on the removal lemma. So again, this is the graph removal lemma again. I want to dwell on it for a moment and discuss the bounds. So the theorem says for every epsilon there exists this row. And I just want to talk about what we know about this row. So let's let rho of epsilon h be the largest possible value of rho such that this theorem holds. And so what can we say about this parameter? So the original proofs of the graph removal lemma gave this really awful bound. They showed that 1 over rho is bounded by a tower of 2's whose height is exponential in 1 over epsilon. Is polynomial in 1 over epsilon, where the polynomial depends on h. And this is because they use Semeredi's regularity lemma, which sort of necessarily invokes these tower type bounds. this bound is really huge. There's been only one improvement to it, which is due to Jacob Fox from about a decade ago. And he was able to improve the tower height from polynomial in 1 over epsilon to logarithmic in 1 over epsilon. So on the one hand, this is an enormous improvement, right? Because even removing 1 from this tower like shrinks the number by a massive amount. But on the other hand, this is still an enormous bound, and this is still very bad. And on the lower bound side, we know very little. So Ruja and Semrady, and then Alon extended this, proved that basically 1 over rho is at least barely super polynomial in epsilon. So it's at least roughly like 1 over epsilon to the log 1 over epsilon. This is only true for non-bipartite graphs. Somehow the whole thing is degenerate for bipartite graphs. So I'm just going to only focus on non-bipartite graphs. Anyway, the upshot I want to draw from this is just that you should remember that this function rho is super polynomial in epsilon for non-bipartite graphs. And this is important for a couple of reasons. So first of all, I told you that we don't know how to prove this result with some simple averaging arguments. And that's sort of reflected in the bounds. Somehow, if you could do some simple averaging argument to prove a result like this, that would probably get you something like polynomial bounds in the parameters, because that's usually how these things go. And the fact that polynomial bounds are impossible is sort of indicative of the fact that really this result sort of requires something hard to prove it. The other thing that I want to say is there's this massive, massive gap between our upper bound and our lower bound. And this really reflects the fact that we just don't understand the removal lemma well. So it's a really fundamental result in a lot of topics, in a lot of areas in combinatorics. And we just don't really understand it well. And that's reflected by this massive gap between the best known lower and upper bounds. And so it'd be a real breakthrough to improve either of these, even a little bit. Okay, so that's everything I wanted to say about the removal lemma. So now I want to start putting this together and tell you about this recent work. So putting together the minimum degree conditions and the removal lemma. So I'm just going to start talking about triangle removal with high minimum degree. And so here's one of the theorems that Jacob and I proved. So the statement, I have it here, but I'll unpack it. So we're in the setting of the removal lemma. We have a graph that has few triangles, and we want to make a triangle free by deleting few edges. But we're also assuming that this graph has high minimum degree. So we're assuming that the minimum degree is at least a third plus alpha times n. And the theorem is that in this case, you'll notice that the parameter we have for the number of edges removed is linear in the parameter for the number of triangles. So in other words, once we have a graph with sufficiently high minimum degree, then actually the removal lemma has linear bounds. So in general, the triangle removal lemma has, these super polynomial bounds are necessary. But once we assume a sufficiently strong minimum degree condition, so at least 1/3 plus alpha times n, then actually we can get linear bounds for the removal lemma, which I think is a pretty surprising theorem. And another thing that's nice about it is that the proof is actually quite easy. So it'll fit on the rest of the slide. So let me just show you the proof. So let's consider any triangle in the graph G. Let's call its vertices v1, v2, and v3. And by our assumption, the neighborhood of each of these vertices is at least a third plus alpha times n, because we assumed this minimum degree condition. And just by the pigeonhole principle, that means that there exists some pair, vi, vj, such that their common neighborhood, the intersection of their neighborhoods, is at least alpha times n, right? Because I have these three sets, each of size 1/3 plus alpha of the whole thing, so two of them must intersect on a set of size alpha times n, just by pigeonhole. And what does that mean? That means that this edge, vi, vj, lies in at least alpha n triangles, right? That's exactly what it means for their common neighborhood to have at least alpha n vertices. So just saying this differently, we proved that this triangle, v1, v2, v3, contained a popular edge. And by a popular edge, I just mean an edge that lies in at least alpha n triangles. So we showed that every triangle in this graph contains a popular edge. And since every triangle contains a popular edge, if I just delete all the popular edges, I must destroy all the triangles. So it suffices to just count how many popular edges there are. And this is pretty easy. So if we have t popular edges, each popular edge lies in at least alpha n triangles. We've counted each triangle at most 3 times. So if we have t popular edges, we must have at least alpha nt over 3 triangles. And we assumed that we had at most rho n cubed triangles. So this is at most rho n cubed. And if you rearrange, you get that the number of popular edges is at most this quantity, 3 over alpha times rho n squared. And the point is we get few popular edges, and by deleting all of them, we destroy all the triangles. So that finishes the proof. And the thing I want to stress about this proof is that it only used these very sort of simple, like averaging pigeonhole type arguments. It didn't require any heavy machinery like the removal lemma or anything like, Semirates regularity lemma or anything like that. And again, this is sort of why we were able to get this linear bound. It's because we were able to use these sort of like easy averaging arguments, we were able to get a linear bound in the removal lemma. Okay, so the natural question when you see a theorem like this is this 1/3 bound tight? So is it possible to get a linear bound on the removal lemma if we assume a weaker condition on the minimum degree? And the answer is no. So another theorem that we prove is that if you have a graph whose minimum degree is just under 1/3, so 1/3 minus alpha times n, then basically getting rid of all the triangles in such a graph is basically as hard as it is for arbitrary graphs. So somehow above 1/3 we have these linear bounds, but below 1/3 we're basically at the setting of just the totally general triangle removal lemma. And in particular, there are these super polynomial bounds in this case. And again, the proof here is actually pretty straightforward. So there's just a simple construction. So let's suppose that you give me some graph G0, which is hard for the general triangle removal lemma. So it has few triangles, but it's sort of hard to delete all of them by deleting few edges. And there's a simple reduction to show that you can assume that this graph is tripartite. And what we're going to do is we're just going to append to it an enormous blowup of a path on 3 vertices. And then we're going to connect it up to this G0 in this way. And what you notice about this graph is that, first of all, it has minimum degree very close to n over 3. And the reason is that this path is almost the entire graph. These parts are really small. So almost every vertex is adjacent to almost 1/3 of the vertices. And additionally, all the triangles in this graph come from actually this part of G0. So basically, the triangle removal properties of this graph are all coming from this G0, and we assumed that this was like a hard graph for the removal lemma. Yeah, so this shows this thing that, if we're below 1/3, then basically we're just essentially the same setting as just for fully general graphs.
So how big is G0?
Yeah, so you want to make this basically G0 will have like alpha n vertices, and this part will have like 1 minus alpha times n vertices. But I want to think here of alpha as a constant. So this is really just a small constant fraction of the vertices.
Okay.
Yeah. Anyway, the point of this is just that what I showed you on the last 2 slides is that if we assume that the minimum degree is at least 1/3 plus alpha times n, then we get linear bounds on the removal lemma. Whereas if we just weaken this to 1/3 minus alpha times n, then suddenly we're in the regime of just general triangle removal, and that is known to require super polynomial bounds. And so put differently, 1/3 is a threshold for when the triangle removal lemma has, let's say, polynomial bounds. Okay, so we've already seen that 1/3 is a threshold for triangles right at the beginning for these structural properties. So I want to talk about sort of the connection this all has. So we can define 3 thresholds for a general graph. So the one that comes up naturally from the discussion that we just had is we can define the polynomial removal threshold of some graph H to basically be the weakest minimum degree condition you can impose, such that the removal lemma for H has polynomial bounds. So for triangles, we saw this was 1/3. Below 1/3, the triangle removal lemma had super polynomial bounds, whereas above 1/3, it had in fact, linear bounds, but polynomial. So this is this polynomial removal threshold. And earlier, I had mentioned these other sort of more well-studied thresholds. So they're called the chromatic threshold and the homomorphism threshold. And this is just what we saw for triangles at the beginning of the talk. So I haven't defined them formally, but roughly the chromatic threshold is the weakest minimum degree condition you can impose such that an H-free graph has bounded chromatic number. And the homomorphism threshold is the weakest minimum degree condition you can impose such that an H-free graph has sort of this bounded structure. There's just a finite set of structures that can appear. And basically, all I've told you so far is that for triangles, all three of these numbers equal a third. So right at the beginning, I told you about these theorems of Erdős, Heinel, Szymonovich, and then Tomasin and Wuchak that showed that there's this structural threshold for triangle-free graphs at 1/3. And what I showed you on the last slide, the last two slides, is that 1/3 is also a threshold for when the triangle removal lemma goes from having super polynomial bounds to polynomial bounds. Okay, and this actually extends. So you could ask, what about removing larger cliques? Or asking about larger cliques. And it's known that the chromatic threshold for KR is 2R minus 5 over 2R minus 3. This is a theorem of Nikiforov. Goddard and Lyle proved that the homomorphism threshold for KR is also 2R minus 5 over 2R minus 3. And Jacob and I prove in our paper that also this polynomial removal threshold for KR is 2R minus 5 over 2R minus 3. So this is the threshold where removing cliques of size R goes from having super polynomial bounds down to polynomial bounds. Okay, so you see the pattern, right? Clearly, these are just equal to one another. Well, no. So it turns out that for K222, it's easy and sort of a folklore result that the chromatic threshold and the homomorphism threshold are a half, whereas we prove in our paper that this polynomial removal threshold for this graph is actually 1/3. So it's not the case that this polynomial removal threshold always equals these other thresholds. So here it might be smaller. Another example is long odd cycles. So Tomasin proved that the chromatic threshold of odd cycles of length at least 5 is 0. Letzter and Snyder, and then Ebsen and Schacht, we don't know what the homomorphism threshold is, but we know it's between 0 and 1 over the length of the cycle. And what Jacob and I prove in this paper is that actually the polynomial removal threshold for these cycles is between 1 over the length and 1/2. We also don't know what it is. But here you see that this polynomial removal threshold can actually be larger than these two thresholds, or at least this one. So in general, this thing really isn't the same as these other ones. But for triangles it is, and for cliques it is. And we don't really know what's going on with that. One other example, I don't expect you to remember all of these numbers or to really internalize their meanings, but let's say that we have a graph whose chromatic number equals its clique number, which is some R. Then Allen, Butcher, Griffiths, Hayakawa, and Morris were able to determine exactly what the chromatic threshold is. It's one of these three numbers, and they can in fact tell you which one it is. It depends on some structural properties of the graph. So it's one of these three. We don't know what the homomorphism threshold is in general, but it's between the chromatic threshold and this top value. And in our paper, we determine that the polynomial removal threshold for this thing is actually this middle value. So in general, the polynomial removal threshold for such graphs, might be the same as the chromatic threshold, but it might be smaller and it might be larger. Yeah, anyway, somehow it's clear that there's some connection going on here. Like, it can't be a coincidence that for triangles we're getting a third, and for cliques we're getting the right answer for both the structural question and for this removal question. But it's not the case that they're just always equal, and it would be amazing to actually understand what's going on. Yeah. Are there any questions about anything on this slide or anything else that I've mentioned?
What do you think what would your guess be? Do you have a guess?
No. I mean, I really don't. It seems that there's something special about cliques that makes it equal to these two. But I don't understand why. Like, so in particular, our proof for triangles that gave this 1/3 didn't use anything related to why these answers are 1/3. And so we don't know any direct connection between this removal problem and these structural problems, besides the fact that the same numbers keep showing up. And so I think in order to even make a guess, I'd have to see some actual direct connection between the problems, besides just the same numbers showing up.
Actually, for the blow-ups of cliques,
yeah.
I mean, K22 is a blow-up of a K3, but
so sorry, go ahead.
True generally, I don't know.
Yeah, so we're able to prove that for a blow-up of a clique, it's always equal to the same thing for a clique. There's actually an even more general result, which is that if I have two graphs, and this one is a subgraph of this one, and there's a homomorphism from this one to the first one, then they have the same polynomial removal threshold. So for blowups, the point is that like a triangle is a subgraph of K222, and there's a homomorphism in the other direction. And so then this graph has the same polynomial removal threshold as the triangle. But things like that just aren't true for these other thresholds.
Oh, okay.
So I had a question in terms of these cliques, these three things being equal. And so the example that you showed for the complexity for this below 1/3, cannot you reuse the same example at least for this homomorphism complexity?
Yes, that's you can basically use the same thing.
Somehow you just take any complex graph and then you wrap it in something.
That's basically correct. So it's a little hard to do it for, you need to do something for triangles where you need to do something for the complex thing for triangles. But then for larger cliques, indeed, you basically just add a bunch of other parts and make it complete. So somehow for these clique results, for the lower bounds, it sort of suffices to understand what's going on for triangles. And then the lower bounds for larger cliques just work by sort of some easy, you build on that, yeah. Yeah. Okay. So the last thing that I wanted to say, and I won't really say in any detail, but I just wanted to say something about how we prove these bounds for the KR removal lemma once you're above this threshold for KR removal. So again, we can get a linear bound for KR removal, where once you're above this threshold and you have few copies of KR, then you can make it KR free by deleting a number of edges that's just linear in this parameter row times m squared. And I won't really say anything about the proof, but as with the case r equals 3, it suffices to find a popular edge. So it suffices to show that every copy of KR contains an edge which lies in basically n to the r minus 2 copies of KR. So once you show that every copy of KR has a popular edge, you can delete all the popular edges and prove this theorem in the same way as before. And the way we do this is kind of tricky, and I won't show it to you. But basically, there's some sort of tricky induction you can do where you start with a KR, and by averaging, you can find r minus 1 vertices that are popular in a certain sense. And then by averaging along those, you can find an r minus 2 tuple that are popular in a certain sense. And by constantly doing this sort of averaging over and over again, you're eventually able to reduce to 2 vertices that are popular in this sense, and that's how you do it. So it's all these averaging arguments again, but just you have to do it sort of iteratively in some nice inductive scheme. And I won't say much more about that. Yeah, and I think just for time reasons, I'll start wrapping up.
Fine.
Sorry?
We have 6 minutes questions, and you can.
Well, I'll wrap up slowly.
Okay.
Yeah, so I just wanted to, I think there's, I want to tell you, just summarize what we've done, because I know I covered a lot of different material. And then also, there's a lot of open problems that I want to leave you with. Okay, so first of all, what did I tell you? The first thing I told you about are these structural thresholds. So for triangles, for triangle-free graphs, there's a structural threshold at 1/3, where above minimum degree 1/3, they have sort of bounded complexity, whereas below minimum degree 1/3, they can have sort of be arbitrarily complex. And our new result is basically a corresponding theorem for the removal lemma, where there's also a threshold at 1/3, where the removal lemma has linear bounds above minimum degree 1/3, whereas it has super polynomial bounds are necessary below minimum degree 1/3. And to go with that, there's also a threshold for like how the proofs look. So once you're above these thresholds, you can prove the removal lemma just by these averaging arguments. For triangles, it was really a pretty easy averaging argument. For larger cliques, you need to do something iterative, but it is still just sort of averaging in pigeonhole. Whereas, below the threshold, we're already again in the setting of general graphs, and there it really seems like some stronger thing, like Semiretti's regularity lemma, is necessary. So there's actually a threshold of 1/3, reflected in the dependencies, whether they're polynomial or super polynomial, but also in the proof techniques that are available, it seems. And then, okay, so this leads us to define this removal threshold, this number at which you go from having super polynomial to polynomial bounds. And we determine it for a lot of graphs, but there's still a lot of open questions. So we proved that, I mentioned this earlier, that if the chromatic number equals the clique number of a graph, then we know exactly what its polynomial removal threshold is. It's exactly this 2r minus 5 over 2r minus 3. But we don't know how to say anything about graphs whose clique number is different from their chromatic number. So, for instance, odd cycles are graphs whose clique number is different from their chromatic number, and we don't know what their polynomial removal threshold is. We get a lower bound of 1 over the length, but we don't know if that's tight. And then the other open question that I think is really interesting, which is what I was hinting at with this big table, is just what's actually the connection between these different topics, between the removal question and these structural questions. I feel like there has to be some connection, because it can't be a coincidence that just the same numbers are showing up. But I don't know what it is, and it can't be a totally trivial connection, because it's not always the case that they're equal. So, there's something going on. So, a good question would be to determine which graphs have their polynomial removal threshold equal to, say, the chromatic threshold, or equal to the homomorphism threshold. Another question I wanted to mention, this is sort of a more broader question, but the removal lemma has a ton of applications all over the place. But many of the applications, you want to use it in fairly sparse graphs. So for instance, if you want to prove Roth's theorem on 3-term arithmetic progressions, you can do this with the triangle removal lemma, but only for pretty sparse graphs. Or you want to apply it to a pretty sparse graph. Are there applications where you get a much better removal lemma if you assume some high minimum degree? So I know of exactly one application. Jacob and I actually stumbled on this problem while working on something else, and we realized that it'd be nice to have a removal lemma with high minimum degree, and then we did this project. But I'd be very happy to see more applications of getting these linear bounds for certain problems within the removal lemma. And one final question that I'd be very interested in is, can you do any of this for hypergraphs? So hypergraph removal is now a theorem, but it's pretty hard. It's a lot harder than graph removal. And can you do anything like this in hypergraphs? So for instance, hypergraph removal under high minimum degree, or determining a threshold or something like this. It's possible this would be a lot harder because a lot of these Turon type questions, like these structural results, are much less well understood in hypergraphs. So I think doing an analog of any of the things I've said in this talk for hypergraphs, I think would be very interesting. And yeah, that's everything I had. So thank you for your attention and for staying up late to listen to me.
Thank you, Yuval. Let's give a round of applause to Yuval. Thanks a lot for a great talk. Okay, questions? That was really nice, like I'll explain.
Yeah.
So did you not try to do anything for graphs at all, or?
For what, sorry?
So for hypergraphs, I mean, did you try at all for any?
I tried a little bit. It's not even clear what the right question is. So for instance, like what kind of minimum degree do you want to assume?
Yeah.
Yes, I mean, I think the easiest, the most natural question to try is to do the thing that I showed you for triangles, to do it for like K43 in a 3 uniform hypergraph. And I mean, it seems, yeah, I mean, somehow the problem that seems to arise was just the most naive thing that I tried is that, you know, I was doing these arguments about the sizes of neighborhoods and like their intersections and stuff like this. Whereas it seems that the most natural thing for hypergraphs would be to like look at links or something like that. And so then I don't know how to do these sort of pigeonhole averaging arguments directly. But it's possible there's some easy analog that I just didn't see. I didn't think about it very hard. Yeah.
But you're not really using anything like the true numbers of the cliques or something, right? Like it's just...
No, you're not. You're certainly not using it explicitly, but it's possible that somehow implicitly you're using the fact that we sort of know types of arguments like this for graphs that might not be available for hypergraphs. But yeah, I don't know. I really don't know, and it might be that there's something easy that I didn't see.
No, it's very interesting.
I actually have a question also. Well, maybe first a very stupid remark about Turan's theorem itself. I guess, I mean, if you think of Mantel's theorem, it also uses a similar pigeonholing, right, in the proof.
That's one way of proving it, yeah.
Yeah, this is one, yeah, so you just like two vertices that have this common, right. Yeah, so so this is, in that sense, this is a superficial kind of connection. But then, of course, for larger cliques, it seems to deviate, kind of, because it seems that your argument is more complicated.
Yeah.
But yeah. Anyway, so what I wanted to ask is about this 1/3 threshold. So the alpha that you were writing there. Is it just a constant alpha, or is there a better understanding on what actually happens at this threshold, kind of?
Yeah, good question. So
for both your situation and for the previous question.
So that's a really good question. So for the structural results, there's actually a lot known at this point. So for instance, Brandt and Thomaset have a really beautiful theorem where they just determine exactly what's going on above the threshold for for these structures that can appear. And basically, so if I try to go back to as you get closer and closer to a third, the number of structures that appear is basically 1 over alpha if you're at a third plus alpha, and they know exactly what the minimal structures are. There's a set of graphs, and they know exactly what they are. Below a third, so the matching lower bound, we understand less well, so we don't know how to really do anything quite to get, you know, so what actually happens is you're getting close to a third from below, we don't understand as well. And for our problem, you know, we can say something. So for instance, in this theorem, you can actually see the dependence on alpha exactly, and it's just linear and 1 over alpha. And similarly for larger removal, we get some pretty nice simple dependence on alpha. And again, from below, it's a little more complicated because we are, for the thing from below, we started with some sort of Oracle gave us this bad graph for the removal lemma, and we don't understand what these bad graphs are. And then the size of this thing we take is like alpha n. So depending on what's actually going on with the removal lemma, which we don't understand, that will affect how the parameter alpha goes into the bounds. But, you know, yeah, if you are willing to take whatever the mysterious triangle removal function is, we understand how alpha is determined just as a function of that thing from below. But Yeah, I think there's still a lot we don't understand. So for instance, if you're actually at a third times n, or maybe a third times n plus something sublinear, like a third times n plus a constant, then our results don't know how to say anything, but it's possible there'd be some interesting things you could say there.
You mean you could maybe say even harder, like, because you already say that it's just as hard as.
Yeah, sorry, I guess I meant above. Sorry, I meant for this theorem maybe. Like if you're above the threshold, if you're at minimum degree like a third times n plus 100, then our result doesn't say anything about the removal lemma at that regime, but maybe you could say something.
Yeah.
I also had a quick question about this applications of high minimum degree removal lemma. So what was the application that you?
Yeah. So right. So the application is something like this. So you can think of like, let's say you have oops, I want to right. So let's say that G has minimum degree at least let's say a half minus epsilon times n, and at most I don't know, rho times n cubed triangles. Then I want to say that G is epsilon close to bipartite. So this is some strange combination of a stability theorem and a supersaturation theorem. So the stability theorem for like Mantel's theorem says that if I assume that I have no triangles and my minimum degree is close to a half, oh sorry, these epsilons shouldn't be the same, maybe that's a delta. The stability theorem says that if I'm if I have close to a half times n edges and I have no triangles, then I'm epsilon close to bipartite. And there's a supersaturation theorem that says that if I'm far from bipartite, if I have a lot more than this edges, then I must have a lot of triangles. And this is some combination of that, where you're below the threshold and you have few triangles. And basically, a way you could prove this is you first apply the removal lemma to delete all the triangles by deleting few edges. And then you apply the stability theorem just now that you have no triangles. But that invokes very bad bounds because you're applying the general removal lemma. But once you have our result, you can actually do this with basically optimal dependencies between all these parameters. Yeah.
Yeah, I wonder if, I mean, now I don't remember exactly, but my feeling was that this kind of down setting removal lemma may be useful for applications of container method.
Oh, interesting.
Really?
Maybe. Well, don't they use this like when counting, I don't know, counting some kind of counting triangle free graphs, for example? Don't they use triangle the removal lemma somewhere on the way?
I don't think so.
For just counting triangle free graphs, you just need the supersaturation result, I think, plus the containers lemma.
It's usually so-called balanced supersaturation, which is slightly finer. Well, not slightly. It's a bit,
Okay, so maybe.
Yuval, is this in the same paper? This?
No, this hasn't come out yet. We're working on wrapping up. Sorry, you mean this result that I wrote here on the last slide? Yeah, so this I don't think is written up anywhere yet. We're working on finishing up the thing we're doing with this.
Also complete NEKR, I assume.
Yeah, it's exactly the same for NEKR. Yeah, I mean, there's other ways of proving this also. That you can get it without with nice dependencies without using any removal by some other arguments that come from these stability techniques. So this specifically isn't the most exciting result in the world, but I just like it because it's an application of this removal with high minimum degree.
It's good. Okay, I think we are now over time, and We can just keep on asking you questions. I'm sure you will answer them also. So good. Okay, let's thank you, Val, and let's thank everyone for their time and all our speakers, Matthew, Shoham, and Yunko.